Hello friends, I am Chetan Ingale, working as an assistant professor in Department of Chemistry, RBNB College, Shirampur. In our last few lectures, we have dealt with what is meant by aryl halide and its properties. Along with that properties, we have also seen about the preparations of aryl halide. Now, in this lecture, we have to study about the reactivity of haloarenes. We know that. Now, while dealing with reactivity of haloarenes, we know that the structure of haloarene, which we have to study in this semester, is nothing but this is haloarene. That is our aryl halide. We know that the carbon atom on which this halogen is present is sp2 hybridized. As this carbon atom has sp2 hybridization, and when we determine the percent of S character present in this carbon, then we know that it has 33.33% of S character. As the percent of S character of this carbon atom increases as compared to the percent of S character present in alkyl halide, here we know that the hybridization of this carbon atom is sp3 and has 25% of S character. And it has how many? 25% of S character. And in case of sp2 hybridization, the percent of S character increases. As the percent of S character increases, its electronegativity also increases. As the electronegativity of this carbon atom increases as compared to the electronegativity of this carbon atom, we may say that sp2 hybrid orbitals has higher electronegativity than this sp3 hybrid orbitals. That's why, as compared to this carbon and halogen bond, the electrons present between this sp2 carbon atom and this halogen atom are tightly bound to this more electronegative sp2 carbon atom. That's why, due to higher electronegativity of this sp2 carbon atom, this halogen atom cannot be easily eliminated from this molecule. It means it cannot be easily substituted. That's why this is the first reason about the reactivity of haloalkenes towards the nucleophilic substitution reaction. It means on the basis of percent of S character of this sp2 hybrid carbon atom, we can say that substitution of this halogen atom from this aryl halide is difficult. Along with that, we also know that the halogen atom also carries a non-bonding electron pair on it, and these non-bonding electron pairs are in delocalization with this pi bond. which are given as this lone pair firstly delocalizes with this pi bond to give the first resonating structure, which is shown as now this negative charge is in delocalization with this pi bond. As like this negative charge now is in delocalization with this pi bond to form the next resonating structure. Now, finally, this negative charge is in delocalization with this pi bond to give our first structure, which is shown as on the basis of all these resonating structures, we know that in each and every canonical form, that is resonating structures, we have seen that there is an formation of carbon halogen pi bonds. Due to the formation of carbon halogen pi bonds in all these structures, we say that the bond between carbon and halogen atom in case of haloarenes becomes strong, and that's why due to formation of partial pi bond due to delocalization, these molecules becomes resistant to nucleophilic substitution reaction. There also haloarenes undergoes nucleophilic substitution reaction. There also this haloarenes undergoes nucleophilic substitution reaction, but to a drastic condition, when if sometimes we increase the temperature or we carried out such nucleophilic substitution reaction on haloarenes at high temperature like 350 degrees Celsius, 250 degrees Celsius, 50 atmospheric pressure, or if such rings has highly electron withdrawing substituent are on it, if highly electron withdrawing substituents are present on haloarenes, then also these haloarenes undergoes nucleophilic substitution reaction, then and then only. So we have to consider the nucleophilic substitution reaction on haloarenes are carried out by using drastic condition, that is by increasing the temperature at high atmospheric pressure. If this is not the case, then we have to increase we have to add the electron withdrawing substituent on this aromatic ring. Now we see some problems. Now we have to see some problems regarding reactions of haloarenes. We know that when this chlorobenzene is treated with a base that is aqueous NaOH. We know that this OH negative ion in this NaOH acts as a nucleophile here. This nucleophile will replaces this chlorine atom when this reaction is carried out only at high temperature and high pressure. That's why this reaction will proceed in forward direction when we heat this molecule at 350 degrees Celsius or at 300 atmospheric pressure. Then and then only we obtain phenol as a product. Then and then only we obtain phenol as a product with the formation of NaCl. If instead of this we have to carry out amination or we have to attack the ammonia molecule on this chlorobenzene, we have to change our reaction conditions. For example, when this chlorobenzene is treated with ammonia molecule, at 250 degrees Celsius and 50 atmospheric pressure, when we carried out what? When the attack of ammonia on this chlorobenzene takes place at 250 degrees Celsius and 50 atmospheric pressure, then we obtain aniline as a product with the formation of ammonium chloride, that is NH4Cl. This is the second reaction. It is the second aromatic nucleophilic substitution reaction. Now next, when this bromobenzene is treated with CuCN, when this bromobenzene is treated with CuCN at 250 degrees Celsius, but in presence of pyridine, then we obtain cyanobenzene as a product. Generally, whatever the reaction we have studied up till now in this head, we know that in each and every case we use the drastic conditions. It means we use higher temperature and higher atmospheric pressure. Okay, this is the reactions of haloarenes regarding nucleophilic substitution reaction. Now, these are the reaction carried out at drastic condition, whereas there are some reactions also in which we cannot use drastic conditions, but instead of that drastic condition we use or we add electron withdrawing substituent on haloarenes. That electron withdrawing substituent will withdraw the electron from the aromatic ring, and due to withdrawal of electron from that aromatic ring becomes electrophilic in nature, or we may say that aromatic ring cannot be remain resistant to electrons or nucleophiles. Okay, one by one we will see some problems regarding the nucleophilic substitution on electron withdrawing substituent containing haloarenes. We know that this is our first structure. that is ortho-nitrochlorobenzene. When this molecule is treated with base like NaOH at 170 degrees Celsius, after the acidification, we know that this NO2 is an electron withdrawing group which withdraws electron from this ring, and that's why this carbon atom on which this halogen atom is present becomes somewhat electrophilic in nature. Due to its somewhat electrophilic nature, this nucleophile will easily attack on this carbon atom, and we will obtain nitrophenol, orthonitrophenol as a product. This is the first reaction in which we just add a single electron withdrawing group on this ring. Instead of this single electron withdrawing group, if we insert two electron withdrawing NO2 group on this ring, what will happen to the condition that we have to see in our next example. When this dinitrochlorobenzene is treated with NaOH, that is aqueous NaOH at 95 degrees Celsius, after the acidification, we will obtain dinitrophenol as a product. When we look at this condition, when we look at both the conditions, we know that as one extra electron withdrawing substituent is added to these haloarenes, the temperature of that reaction will obviously decrease. This reaction is carried out at 170 degrees Celsius, whereas this reaction is carried out at 95 degrees Celsius. Now, if we add 3 nitro group to haloarenes, what will happen to that reaction? That also we have to see in our next example. When we add 3 NO2 group, 2 at ortho position and 1 at para position. This is the trinitrochlorobenzene. When this trinitrochlorobenzene, which carries how many? 3 strong electron withdrawing group, there is no requirement of increase of temperature. It means it is this reaction generally carried out by using warm water only. Warm water only followed by acidification. It gives the formation of trinitrophenol. This is all about the reactions of haloarenes, in which up till now we have studied about the nucleophilic substitution reaction which are carried out on these haloarenes, how they will be used or they will be prepared from various conditions. Thank you.